Now let us understand the Newton's law of gravitation, that is universal law of gravitation. It states that the every particle in the of matter in universe attracts every other particle with a force that is directly proportional to the product of the masses and inversely proportional to square of the distance between them. Here focus on the word that every particle of matter. So the law of gravitation is defined for particles of matter. The matter, that means it is having some mass. The law of gravitation is not defined for massless particles. That means to act the gravitational force between two particles, the two should be mass particles. For example, there are two particles of mass m1 and m2 separated by distance r. So according to the Newton's law of gravitation, the attractive force between them is directly proportional to product of the masses, that is m1 into m2, and inversely proportional to square of the distance, that is r square. If we change this proportionality into equality, then we will get F is equals to G m1 m2 upon r square. This G is the universal gravitational constant. If we write this force in the vector form, it can be written as G m1 m2 upon r cube divided by r cap. R cap is the direction of this position vector between m1 and m2. The value of G is 6.67 into 10 power minus 11 Newton meter square per kg square. Now let us see some properties of the universal law of gravitation. So let us see now properties of gravitational force. The first property is it is always attractive in nature. You will never hear that a body is repelled due to a gravitational force. The objects are always attracted because of gravitational force. So it is always attractive in nature. The second property is it is the weakest force in nature. As we have seen that the force is product of mass, that is F is directly proportional to m1 m2 and inversely proportional to distance square. We put the value of constant, that is 6.67 into 10 power minus 11. As the value of this gravitational constant is very much less, that is 10 power minus 11, the force of gravitation will have very less value. So it is the weakest force in nature. The third property is the G. It is the universal gravitational constant, that is gravitational force of attraction between two bodies is not affected by the presence of the other nearby bodies or the medium between them. That means the gravitational force does not depend upon the medium between two particles. For example, two particles of mass m1 and m2 are kept in air at certain distance apart. in this situation the force is F between them. Now if these two particles, this whole system is kept in water, then also the force will be same, because the mass is constant, we have kept the distance constant, and the universal gravitational constant is same everywhere. So the gravitational force is independent of the medium between particles. The fourth law states that, the fourth property says, it follows inverse square law. That means F is inversely proportional to R square. So as distance increases, the value of gravitational force will decrease. The next property is, it is independent of presence of other mass particles. Let us say there are two particles m1 and m2. The distance between them is r and force of attraction between them is F. This is the first scenario when there are only two particles. Now let us see the other case in which there are other mass particles m3, m4, m5, etc. surrounding these two particles. Now in the first case, when only the two mass particles were present, the force of attraction was F. In the second case, when the other mass particles are present, the force will remain same. So the force of attraction depends only on the two mass particles. It is independent of presence of other mass particles. But the net force on given mass particles will change. We will see this situation in the principle of superposition. The next property is, it is central force. So the two bodies attract each other always towards the center of their bodies. For example, there are two spherical bodies of mass m1 and m2. So the gravitational force between them is attracting these two bodies towards their center. In the case of Earth also, it always attracts every particle towards its center and not towards its surface. The next property is, it is conservative force. The meaning of conservative force is that the work done by it in closed loop is zero. So work done by gravitational force in a closed loop is zero. That means it is a conservative force. The next property is, the direction of force is along the line joining two mass particles. If there are two mass particles m1 and m2, then they will attract each other along the line joining two particles. The next property is, we have seen that the universal law of gravitation says that every particle in this universe, focus on the word particle, that means it is defined only for particles. However, if we want to apply this law of gravitation to the larger bodies, then the condition is that the distance between them should be very large as compared to their sizes. In that case, we can apply law of gravitation to the celestial bodies also, because let us say Sun and the Earth, the distance between them is very much greater than either of the Sun or Earth's radius. So we can apply Newton's law of gravitation in this case. Now let us see gravitational force in vector form. There are two mass particles m1 and m2 kept in a xz plane. The position vector between them is r. The position vector of individual mass particle is r1 and r2. The force of attraction will be same for both the bodies. The force applied by m1 on m2 is equals to the magnitude of force applied by m2 on m1, but the direction will be opposite. So they will apply same force but in opposite direction. m1 will attract m2 in this direction and m2 will attract m1 in this direction. As they have same magnitude, opposite direction, and since they act on two different bodies, they form an action-reaction pair. So we can write F12 is equals to minus F21. F12 is force on 1 by 2 and F21 is a force on 2 by 1. This negative sign shows the opposite direction. Now let us see some examples based on Newton's law of gravitation. In this example, what will happen to gravitational force between two bodies if they are brought closer by half of their initial separations? Let's say two bodies have mass m1 and m2 initially between them, and distance between them is r. The force in that case is F. Now they are placed at half of the distance, that is r by 2. We want to find the force F dash in this case. We can write that F is directly proportional to product of mass and it is inversely proportional to square of the distance between them. Here mass particles are not changing, so we can write that force is inversely proportional to r square. So F dash by F will be equal to r divided by r by 2 whole square. So that will be equal to 4. So now the distance, if distance between the particles is reduced by half, then force will become 4 times as that of original force. In the next example, by what percent will the gravitational force between the two bodies be increased if one of their mass is increased by 50% and the other is decreased by 50%? One is increased by 50% and another is decreased by 50%. Let's say there are two mass particles of mass m1 and m2 and they are placed at distance r. In that case, the force of attraction between them is F. Now one of the mass particles' mass is increased by 50%, so the mass will be 1.5 m1, and another is decreased by 50%, so that will be 0.5 m1. Nothing is mentioned about distance, so we have to keep the distance same as r. In that case, the force acting is F dash. We want to find the percentage change when the masses are changed. We know that Newton's law of gravitation says that F is directly proportional to m1, m2. So we can write F dash by F is equals to 1.5 m1 into 0.5 m2 divided by m1 m2. This m1 m2 will get cancelled out. So F dash by F is equals to 3 by 2 into 1 by 2, that is equals to 3 by 4. So F dash is equals to 3 by 4 F. Now percentage change is given by F dash minus F upon F into 100%. So 3 by 4 F minus F divided by F into 100%. So minus 1 by 4 into 100%, that will give us the answer 25%, but minus. Here the minus sign shows that the force is decreased by 25%. In this example, two particles of equal mass move in a circle of radius r under the action of their mutual gravitational force. If the mass of each particle is m, then what is the speed of each particle? Let's see. There are two particles m and m. They are moving in a circular path of radius r. So the distance between two mass particles will be 2r. Now they are revolving in this circular path due to their mutual gravitational force. So the force between two particles, that is centripetal force, will be mv square by r, and it is provided by the gravitational force between two particles, that is equal to gmm into distance between them is total 2r whole square. This m will get cancelled out, so v square by r is equals to gm upon 4r square. So v will be equal to under root gm upon 2r. So this will be our final answer. In the next example, if mass m split into two parts, that is small m and the remaining will be capital M minus small m, which are then separated by a distance, then the ratio of m by m, so that the maximizes gravitational force between the two parts is, here to have the maximum force of gravitation between the two particles, the product of them should be maximum. To have the maximum product, it should be divided into two equal parts. So m should be equal to m minus m. So the small m will be equal to m by 2. We want the ratio small m divided by capital M, that will be equal to 1 by 2. In this example, a particle of mass m is placed at a distance d from one end of uniform rod with length L and mass capital M as shown. We want to find the magnitude of gravitational force on the mass particle m. Here there is one particle and one is rod. The formula that we know is applicable only on the particles, or the distance between the particles is very much greater than the size of the object. but it is not the case in this, so we have to do integration. Let us consider an elementary mass dm of length dr. We have considered an elementary mass dm of length dr at distance r from this mass particle. We will find the gravitational force on m due to this dm, and then we will integrate all the forces acting due to whole rod. The rod has uniform mass distribution, so the mass of this small particle we have considered is given by dm is equals to m by l dr. Due to this small mass particle, small force df will be equal to gm dm upon distance r square is equal to gm. Small dm can be written as m by l into dr. This is a force due to small mass element we have considered. Now to find total force we have to integrate this. So the total force F on the mass particle will be integration of gm m upon l r square dr. The limits will be from initial distance d from d plus l. F will be equal to, here gm m and l are constant, so gm m upon l integration 1 upon r square dr, limits from d to d plus l. Simplifying this, the F will be gmm upon L into integration of 1 divided by R is 1 divided by R square is 1 by R, limits from D to D plus L. So F will be equal to gmm divided by L into 1 upon d plus L minus 1 upon L. So the gravitational force will be gmm divided by d into L plus d. So this will be our final answer. Now let us see how Newton combined the laws of motion with Kepler's law of planetary motion to find or to derive Newton's law of gravitation. For that, he made a simple assumption that the planets are revolving in circular orbits. The time period will be 2 pi r upon v, where r is the radius of orbit. Now we know from the Kepler's law that t square is directly proportional to r cube. So we can write t square is equals to kr cube, where k is the constant of proportionality. Let's say this is equation 1 and this is equation 2. From 1 and 2 we will get 4 pi square r square upon v square, that is time period square, is equal to k r cube. So we can write v square is equals to 4 pi square divided by k r. Now we know that an object in a circular path is accelerated and it is having centripetal acceleration AC as v square by r. So centripetal force will be equal to mv square by r. Put the value of v square over here, we will get 4m pi square divided by kr square. From this we can write that force is inversely proportional to r square and force is directly proportional to m. Now force on the planet due to sun is equals to force on the sun due to planet. That is, force on sun is equals to force on earth. If force is proportional to mass of planet, it should be proportional to mass of sun also, because the force is same for both. So we can write that F is directly proportional to m, where capital M is the mass of sun and small m is the mass of earth or whatever the planet we are talking about. So from this we can write combinedly F is directly proportional to mm upon r square. So F will be equal to gmm upon r square. So in this way Newton combined the laws of motion and Kepler's law to derive the gravitational force formula. Now what will happen when multiple mass particles are present? We want to find the net force, net gravitational force on a single particle. In this case, we will use the principle of superposition of gravitational forces. Let's say there are 4 mass particles in the given system, m1, m2, m3 and m4. The distance between m1 m2 is r12, distance between m1 m3 is r13 and distance between m1 m4 is r14. We want to find the net force on mass m1 due to this forces m2, m3 and m4. The force of attraction on m1 due to m2 is given by F12 and it will be directed along m2. The force due to m3 will be directed along m3 and that will be F13. The force due to m4 will be directed along this line of r14 and its value is F14. To find the net gravitational force on m1, we will add individual forces vectorally. We will have that vector addition. So F net can be given as vector F12 plus vector F13 plus vector F14. So F net will be equal to G m1 m2 upon r12 square into r12, if we are writing in vector form, r12 cube into r12 cap plus g m1 m3 upon r13 whole cube into r13 cap plus g m1 m4 divided by r14 whole cube into r14 cap. Now let us see one example based on the principle of superposition. In this example, three equal masses 2m each are placed at the vertices of an equilateral triangle of side 1 meter. What is the force acting on a mass m placed at a centroid? Here, let us first draw the diagram so that we can understand the situation properly. This is an equilateral triangle of side 1 meter. The mass of 2m is placed at every vertices. We want to find a force on mass particle m placed at the centroid. Here, let's see the distance of the centroid from each vertices is x. Now, the force due to all of three will be having same magnitude. Let's say F1 is equals to F2 is equals to F3, and that is equal to G 2m into m upon x square. So force will be equal to 2gm square upon x square. Now talking about the directions. Force due to this 2m particle will be in this direction, due to this 2m particle will be in this direction, and due to this upward particle will be in vertically upward direction. As it is equilateral triangle, this angle will be 30 degree, this angle will also be 30 degree. So this angle will be 120 degree. If we find resultant of these two have same magnitude of f and angle between them 120 degree. When the magnitude of two vectors is same, then resultant will be along their angle bisector. So this will be the resultant at angle bisector. If the angle between two identical vectors is 120 degree, then the resultant is also having same magnitude, because when the magnitude of two vector is same, then the magnitude of resultant vector is given by 2f cos theta by 2. Here theta is the angle between two vectors, that is 2f cos theta is 120 divided by 2 cos 60 degree. So 2f into cos 60 is 1 by 2. This 2 will get cancelled out, so f will be net will be equal to f. If we draw the resultant of this 2 in this diagram, then we will get that the resultant is exactly in vertically opposite direction f. Magnitude of this is also f. So this 2 will cancel out each other. So net force on particle of mass m will be 0. Now in the same case, same question, what is the net force on mass m if the mass at one of the vertex is quadrupled? It was having mass of 2m on each the vertices, 2m, 2m and 2m. One of the mass is quadrupled, so that will be 4 into 2m. Now in this case we want to find the net force on mass of particle m. Here we can solve this question by two methods. The method 1. These two forces will have same magnitude, F1, and let's say this is also F1. They both are at an angle of 120 degrees, so the resultant will be along this direction, that is equal to F1 only, because angle between them is 120 degree. The force due to the third mass particle will be along this direction, let's say that is F2. So the net force will be magnitude of F2 minus F1. Now let us write the magnitudes of F2 and F1. This is X, let's say. So F1 will be 2m square into g divided by x. X is the distance of centroid from the vertex, that will be 1 by root 3 in this case, 1 by root 3 whole square. So F1 will be equal to 6 gm square. Now let us write the force value of F2. That will be equal to 8 into m, so 8 gm square divided by 1 by root 3 whole square. So it will be 24 gm square. So F net will be equal to 24 gm square minus 6 gm square. So that will give us the answer 18 gm square. And this force will be directed along the direction of force F2. So this will be the direction of F net. Now let us solve this question by another method. Solving this question by other method, let's say this is method 2. Mass 2m, this is quadrupled, so that will be 4 into 2m. This is 2m and this is also 2m. Mass here is m. This distance is 1 by root 3. Now at this place there is total mass of 8m. For this 8m we can write it as 2m plus 6m. We can consider that there are two mass particles at this point. One is of mass 2m and another is of mass 6m. If only 2m mass particle was present, then the net force at the centroid will be 0, that we have seen in the first part of the question. So the contribution of this 2m in the force will be cancelled out by the forces of these two particles. So the responsible mass is only 6m. So we can understand that the force on m is due to only a 6m mass particle placed at this vertex. So F will be equal to G m1 m2, that is 6m into 6m divided by r square, that is 1 by root 3 whole square. So F will be equal to 6 into 3 gm square. So F net is equal to 18 gm square. We are getting same answer with both methods. In this example, two bodies A and B having masses m and n times m are kept at a distance of d. A small particle of mass m is to be placed so that net gravitational force on it is 0. what will be its distance from A? This is A mass particle. A third particle of mass m is to be placed in such a way that the net gravitational force on this particle should be 0. Let's say it is located at a distance of x from A, so the distance from nm should be equal to d minus x. To have net force 0 on mass particle capital M, the force on m due to both of this particle should have same magnitude and opposite direction. This m will attract it in this direction and this will in this direction. So directions are opposite. Now we want to have same magnitude. So compare the magnitudes of force exerted by m and nm. So we can write force between these two particles is gmm upon x square is equals to gnmm upon d minus x whole square. This gmm will get cancelled out, so 1 upon x square is equals to n upon d minus x whole square. Taking square root on both the side, 1 by x will be equal to root n divided by d minus x. Cross multiply it, so we can write d minus x is equals to root n x. So d will be equal to root n plus 1 into x. So distance from particle A will be x is equals to d upon root n plus 1. In this example, we want to find the position from mass 4m at which the net gravitational force due to 4m and 16m is 0. So there are two mass particles of mass 4m and 16m. Let's say distance between them is 2 meters. Given d is equals to 2 meters. So we want to find the position from 4m. Let's say this position is A, on which capital mass m we have assumed that is kept. The distance from 4m is x. So distance from 16m will be 2 minus x. To have 0 force at point A, the magnitude of both the forces should be same. So g 4m into m divided by x square is equals to g m into 16m divided by 2 minus x whole square. This g m will be cancelled out. So 1 upon x square is equals to 4 upon 2 minus x whole square. Taking square root on both the side, 1 by x is equals to 2 upon 2 minus x. So 2 minus x will be equal to 2x. So 2 will be equal to 3x. So x will be equal to 2 by 3 meter. If we want to find the position from mass 16m, that will be 2 minus x, that is equals to 2 minus 2 by 3, that is equals to 4 by 3.